Alright, in this video we're going to wrap up Chapter 7. And in Section 7E we're going to be dealing with counting and probability. Here in this unit we're going to introduce a few counting tools that will enable us to consider a wider range of probability problems. Now to begin with, we're going to start off with a short review of something called factorials. Okay? Products of the form 4 times, 3 times, 2 times 1 come up so frequently in counting problems that they have a special name. Whenever a positive integer n is multiplied by all the preceding positive integers, the result is called n factorial and is denoted by an n with the exclamation mark. Now that exclamation mark is read as factorial. So for example, if I have 1 factorial, it's going to be equal to 1. 2 factorial means 2 times 1, which will be 2. 3 factorial means 3 times 2 times 1, which is 6. 4 factorial means 4 times 3 times 2 times 1. That will be 24, and then 5 factorial means 5 times, 4 times, 3 times, 2 times 1, and that will equal 120. Okay, now in general, n factorial means this. It's going to be n times n minus 1 times n minus 2 times, and so on all the way down to times 2 times 1. Okay, so note that n factorial grows rapidly with n. For example, 20 factorial would mean 2.4 times 10 to the 18th power. 40 factorial is approximately 8.2 times 10 to the 47th power. 60 factorial is approximately 8.3 times 10 to the 81st power. In fact, factorials quickly become so large that many calculators cannot handle them above n is equal to 69 if the calculator limit is 10 to the 100th power. Note also that by definition, 0 factorial is automatically going to be equal to 1. So here we're going to look at some examples here on the right. Here we're going to calculate each of the following without the factorial key on your calculator. There is a factorial key on the 83 and the 84 plus calculator, but we're going to try to do these without using the calculator. Like 6 factorial divided by 4 factorial. The way we can write that out as this. We can do 6 times 5 times 4 times 3 times 2 times 1 for 6 factorial. And then 4 factorial will be 4 times 3 times 2 times 1. And as you can see, we can divide out the like terms in the numerator and the denominator. Here, the 4 divides out, 3 divides out, 2 divides out, and the 1 divides out. So you're left with, in this case, 6 times 5 times 30. 6 times 5, which will end up being 30. So 6 factorial divided by 4 factorial will give you 30 as the final answer. Now in part B, we got 25 factorial divided by 22 factorial. Now unfortunately, you don't want to write 25 factorial as 25 times 24 times 23 all the way down to times 2 and times 1. That can be time consuming. Here, this calculation will be easier if we recognize that 25 factorial would be 25 times 24 times 23 times 22 factorial. Because if you look in your denominator, we already have 22 factorial. So we could write it like this and then divide out the 22 factorial. And just multiply 25 times 24 times 23, which would give you 13,800. And part C, we got 200 factorial divided by 199 factorial. Now, if we try to do 200 factorial on the calculator, you'll probably get an error message because it is too large for most calculators to handle. But this calculation is easy if we recognize that 200 factorial can be written as 200 times 199 factorial, because we already got 199 factorial in the denominator. So we can write it like this. And here, the 199 factorial divides out. You're only going to be left with 200. Okay, now let's look at some examples that are related to factorials and how we can simplify them. Okay, like in these two examples here, there are more on the next page. Let's say I want to simplify 9 factorial. Well, if I write 9 factorial out as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And using my calculator, I'm going to do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and hit enter. You're going to end up with 362,880 as the answer. That's what 9 factorial is equal to. And in example 2, if I have 7 factorial, well, I can expand that as 7 times 6 times 5 times 4 times 3 times 2 times 1. Type all that in, you'll get 5,040. So 7 factorial is equal to 5,040. Alright, now let's look at some more advanced examples that are related to factorials here. Let's say I want to evaluate 13 factorial divided by 10 factorial. 13 factorial divided by 10 factorial. Well, let's look at this. If I expand 13 factorial as this, 13 times 12 times 11 times 11 and then times 10, and I stop at 10 and just say 10 factorial, I'll be done, because notice in the denominator I do have 10 factorial. And in this case here, my 10 factorials divide out. And then I'll just multiply 13 times 12 times 11 to get my final answer of 1,716. Alright, example 4. Let's say we got 13 factorial divided by 10 factorial times 3 factorial. Okay, that 13 factorial, just like I did in example 3, I can write that out as 13 times 12 times 11 times, and I can stop at 10 because I got 10 factorial in the denominator. Now for the 3 factorial, I'm just going to have to expand this as 3 times 2 times 1. Now what I can divide out are the 10 factorials here. Let's see, if I multiply 3 times 2 times 1, that's going to give me 6. So that 6 can go into this 12 2 times. Let's see, 3 times 2 times 1, that's 6. 6 can go into that 12 in the numerator 2 times. I can divide that out. So I'm going to have 13 times 2 times 11. That would give me 286. So the answer for that expression would be 286. Okay, let's look at some more of these. And if I can pull the paper up, here we go. Let's say we want to evaluate 18 factorial divided by 4 factorial times 18 minus 4. That quantity will be factorial. In this case, I need to simplify what's in the parentheses here. So I'm going to bring over the 18 factorial divided by 4 factorial. And then if I do 18 minus 4, I'm going to get 14. So I got 14 factorial in the denominator. Alright, and now let's go ahead and expand this and simplify it as we possibly can. 18 factorial will be something like 18 times 17 times 16 times 15. Now I'm going to stop at 14 and say 14 factorial. And the reason for that, because in the denominator I already got 14 factorial. I need to expand 4 factorial as this. 4 times, 3 times, 2 times, 1. And then that's multiplied by 14 factorial. Now when I simplify this, the 14 factorials are gone. Let's see what else I can get rid of here. Let's say if I divide this 4 into the 16, that's in the numerator, that's going to go 4 times. Well, I know 2 times 1 will be 2. If I divide the 2 into that 18, it'll go 9 times. And the 3 in the denominator, if I divide 3 into 15, that's going to go 5 times. So you might want to do some cross dividing as much as you possibly can, if you can. So I'm going to be left with 9 times 17 times 4 times 5. You'll end up with 3060. And that will be the final answer for that expression. Alright, next we'll look at example 6. We got 16 factorial divided by 3 factorial times the quantity 16 minus 3 factorial. Well, let's simplify what's in the parentheses here. Bring over the 16 factorial, and then in the denominator 3 factorial. 16 minus 3 will be 13. So I have 13 factorial in the denominator. Now I'm going to expand 16 factorial in the numerator as 16 times 15 times 14 times, and I can stop at 13. Because in the denominator I do have 13 factorial here. I'm going to expand the 3 factorial as 3 times 2 times 1. Bring that 13 factorial over. You're going to see that the 13 factorials divide out. And, let's see, 2 times 1 will be 2. That 2 goes into 14 7 times. This 3 can go into 15 5 times. So I'm going to have 16 times 5 times 7, which will give me a final answer of 560. Okay, so that's just a brief review of what factorials are and how to evaluate expressions with factorials in them. Alright, next we're going to talk about arrangements and with repetition. Need to bring this down. Okay. If we make all selections from a group of n choices, a total of n times and so on times n, which is equal to n to the r, different arrangements are possible. Like in example 7. Here we're going to answer the following question using the appropriate counting technique, which may be either arrangement with repetition, permutations, or combinations. Be sure to explain why this counting technique applies to the problem. How many different 5-digit codes can be formed using digits 0 through 9? Now, here we have 10 digits, 0 all the way up to 9. And we want 5-digit codes. How many different 5-digit codes can we form? Well, the first number would be 10. We can choose 10. For the second number, we have 10 numbers to choose from. The third number, again, 10 numbers to choose from. The fourth number, 10 numbers to choose from. And the fifth digit, 10 numbers to choose from. Not 110. And that's, of course, 10 to the 5th power, which would be, in this case, 100,000. If you evaluate 10 to the 5th, it'll be 100,000. So here, we have to use arrangements with repetitions because there are selections from a group of n choices, and choices can be repeated. So I can just go ahead and fill this out. There are 100,000 possible 5-digit codes. Okay. All right, next we'll look at permutations. Here we're going to be dealing with permutations whenever these occur. All selections come from a single group of items. No item may be selected more than once, and the order of the arrangement matters. Okay, so for example, A, B, C, D is going to be different from D, C, B, A. So the order does matter. And no item may be selected more than once, and all the selections come from a single group of items. So here, the total number of permutations possible with a group of n items is n factorial, where n factorial will be n times n minus 1 all the way down to times 2 times 1. Okay, so in this example that I'm going to show you, here we're going to answer the following questions using arrangements with repetition, permutations, or combinations. Be sure to explain why the particular counting technique applies to the problem. How many different 8-digit passwords can be formed from the numbers 1 to 8 if repetition is not allowed? Okay, so we know it's got to be a permutation type problem because, well, actually it's arrangement if you look at it, because no item may be selected more than once and the order does matter. I take that back. That is a permutation problem. Okay? No item may be selected more than once and the order does matter. So here, it's this one. And we're going to calculate how many different passwords are possible. So here, that's going to be 8 factorial, which is going to be, in this case, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Multiply all that out, that will give you 40,320. 40,320 different passwords are possible. Okay. Okay, now let's look at our permutations formula. This is where you make R selections from a group of n items. The number of permutations or arrangements in which the order matters is going to be this. The notation for that will be NPR. So here NPR is going to be equivalent to n factorial divided by n minus 1 factorial. And here they're using n times n minus 1 times n minus 2 times, and so on, all the way down to n minus r plus 1. And here NPR is read as the number of permutations of n items taken r at a time. Okay, that's what that means. Okay, let's look at example 9, where we can use that permutations formula here. Here we're going to answer the following question using arrangements with repetition, permutations, or combinations. Be sure to explain why the particular counting technique applies to the problem. Here, a city council with 5 members must elect a 4-person executive committee consisting of a mayor, deputy mayor, secretary, and treasurer. How many executive committees are possible? Okay. So here you can see this is going to be a permutation problem, and that's because no item may be selected more than once and the order does matter. Okay. So here we're going to calculate the number of different committees that are possible using NPR. Now your N is going to be, in this case, the number of members here. In this case, it's going to be 5. Then your P, and we're choosing a 4-person executive committee. So it'll be 4 here. 5P4, and then we use that formula that I just showed you. Here, the numerator is your N, so it'll be 5 factorial. That's this number on the left, divided by n minus r factorial. N is 5, r is 4. So it'll be 5 minus 4 factorial. Okay, bring over the 5 factorial. That's going to be divided by 5 minus 4 will be 1. So I got 1 factorial. Now I'm going to expand the 5 factorial as 5 times 4 times 3 times 2 times 1. And 1 factorial is just simply going to be 1. And of course, not that it matters, the 1 divides out. You'll have 5 times 4 times 3 times 2, which will end up being 120. So in this case here, you're going to have 120 different committees that are possible. Okay. And here's another example of this. Answer the following question using arrangements with repetition, permutations, or combinations. How many anagrams or rearrangements of the letters CAM phone can you make? Well, we're looking at rearrangements, so here we got to do that in factorial business, and here your n is going to be 8 factorial, which is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now here we can't use permutations because we're not selecting an arrangement of some number, okay? Because permutations call for our selections from a group of n items, okay? Now if I multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, I'm going to end up with 40,320. So all the letters can be arranged in 40,320 ways. Okay. Alright, now we're going to talk about combinations here. Now here combinations occur whenever all selections come from a single group of items, no item may be selected more than once, and the order of the arrangement does not matter. So for example, ABCD is considered to be the same as DCBA. So now, if we make our selections from a group of n items, the number of possible combinations is going to be this. Here you're going to have NCR, and that's going to be equal to NPR divided by R factorial. And this will be equal to n factorial divided by n minus r, that quantity will be factorial, times r factorial, where NCR is read as the number of combinations of n items taken r at a time. So in example 11, answer the following question using arrangements with repetition, permutations, or combinations. Be sure to explain why the particular counting technique applies to the problem. In this case here, Dog Shelter is giving away 8 different dogs, but you have room for only 3 of them. How many different dog families could you have? Okay. So here the arrangement does not matter in this case. So we have a combination problem. I'm going to do this at the bottom. So the NCR, your N is going to be 8 different dogs, so that's going to be 8C, and you only have room for 3 of them. That's your R, 8C3. So in this case here, this will be n factorial. Your n is 8, that'll be 8 factorial, divided by n minus r. N is 8, r is 3. So it'll be 8 minus 3 factorial times r, which is 3 factorial. So I'm applying that combinations formula that we just saw. Here it is right here, to that particular problem. Now let's simplify all of this. Bring over the 8 factorial. In the denominator, 8 minus 3 will be 5, so this will be 5 factorial times 3 factorial. Now if I expand this out, let's say 8 factorial. That's 8 times 7 times 6 times 5. Now I'll stop at 5 with 5 factorial because the denominator has 5 factorial in it. And then that 3 factorial will be expanded as 3 times 2 times 1. Now if I divide out the 5 factorial, if I multiply 3 times 2 times 1, that's 6. That product can divide out with that 6 in the numerator. So 8 times 7 is all I have left, which will give me 56. So there are 56 different dog families that are possible in this case. Okay, and finally, a final example in this video. A certain lottery has 36 numbers. In how many different ways can 6 of the numbers be selected? Assume that order of selection is not important. So here the order is not going to be important, so that tells me we have a combinations problem. So here we got to use NCR. Your N is going to be 36, and then you get to C, and we're finding out how many ways can 6 of the numbers be selected. That's your R, 6. Okay? So now, using the combinations formula that I showed you, n factorial, that's going to be the 36. since n is 36, so 36 factorial divided by n minus r, that'd be 36 minus 6 factorial. That's going to be multiplied by the r, which is 6, so it'll be 6 factorial. Okay. Now let's go ahead and simplify this. Bring over the 36 factorial, subtract 6 from 36, you're going to get 30. So that's 30 factorial times 6 factorial. Now I'm going to expand 36 factorial as 36 times 35 times 34 times 33 times 32 times 31, and I will stop at 30 because the denominator does have the 30 factorial, which I can divide out. And I'm going to expand 6 factorial as 6 times 5 times 4 times 3 times 2 times 1. So in this case here, I'm going to go ahead and divide out the 30 factorial in the numerator and the denominator. Let's see. If I multiply this 6 times 3 times 2 times 1, that product will give me 36. These numbers, the 6 and the 3 times 2 times 1, I can divide out with that 36. And then this 5 can divide out with the 35. So 5 goes into 35 7 times. And let's see here. That 4 can go into this 32 8 times. So I'm going to be left with, in this case, 7 times 34 times 33 times 8 times 31. And this will be the final answer there, 1,947,792. Oops. 1,947,792. So in this case here, there are 1,947,792 different ways the numbers can be selected. Okay. Alright, so that's going to complete this video on counting and probability. And that also wraps up Chapter 7 dealing with probability, living with the odds.